Previously, we have discussed about the nature of light, and now in this part, we are going to discuss about what is optics and what are the methods that we do optics. So, what is optics? Optics is the science of light. It describes the behavior and properties of light and the interaction of light with matter. So in short, it's about what light is made of and how it behaves. A related branch of optics is photonics, which is the technology of creating and using light. Now, we can classify optics into two major branches: classical optics and quantum optics. Now, classical optics is mainly based on the electromagnetic theory of light, whereas in quantum optics, we consider light to be as photons, which have both wave-like and particle-like properties. In most cases of optical phenomena, we can ignore the quantum properties of light and accept that light is an electromagnetic wave. Now, there are two branches of classical optics: geometric or ray optics and physical or wave optics. You are most likely aware of both these branches of classical optics. Remember the ray diagrams that you used to draw to locate the position of the images of simplified objects? And the concepts of wave that you have used to understand interference and diffraction. Now, have you wondered why there are two ways of doing classical optics? Why not just use a single way? Why not just treat them as electromagnetic fields? Well, let's find out why. Now, it's true that in classical optics, we consider light to be electromagnetic wave. And most of the optical phenomena that are relevant to the study of optics actually can be explained by using classical electromagnetic description of light. So the fact that light can be considered a kind of wave may seem a good news to you, as you may already have known how to deal with the waves. The logical approach to take then is to derive the wave equation for light and then solve it for different boundary conditions in different ways to explain the different optical phenomena that we see around us. But it's easier said than done. Actually, it's very difficult to apply this process in practice. There are only a very limited number of cases actually where we can apply this and solve the wave equation analytically. In the majority of the cases, we can't even write down the solutions. So this is what prevents us from doing optics as an electromagnetic field theory. Practical optics is done by using simplified models that are easy to apply. Now, geometric optics model is one of those models. It is the most simplified model that we use in optics. In this model, light is considered to be a collection of rays which travel in a straight line and bend when they pass through or reflect from some surfaces. Another important assumption of geometric optics is that light rays can cross without influencing each other. Now, you may wonder, how can we treat light as collection of rays whereas they are electromagnetic waves? How can waves be a collection of rays? Well, they are not the same. But the wave nature of light only becomes significant when we are dealing with optical elements that are comparable to the size of the wavelength of light. So ray optics can be a very good approximation of physical optics that is applicable when the wavelength of light is much smaller than size of the optical elements that we are considering. Now let's turn our concentration to physical optics. It is a relatively more comprehensive model of light, but still it's not the actual classical theory of light, because the actual theory is much more complicated and is not practically applicable in most cases. This physical optics is an intermediate method between geometric optics and the full electromagnetic wave. Geometric optics fully ignores the wave effects. On the other hand, electromagnetism is a very precise theory, and physical optics is something in between. So in physical optics, lights are wave but not as complicated as the electromagnetic field. So the physical word here means a little bit more physical than ray optics, but not the exact physical theory of light. Using this physical optics, one can explain diffraction and interference of light, which geometric optics cannot. So when does physical optics become more applicable than geometric optics? Well, when we are dealing with optical elements that are comparable to or smaller than the wavelength of light that is used. But still, there are quite a few optical phenomena that can be explained by using classical electromagnetic theory. In these cases, both wave-like and particle-like properties of light need to be taken into account. To explain this kind of behavior, quantum mechanics is required. In quantum theory, light is considered to be a collection of particles which are known as photons. So, in quantum optics, what we do is apply quantum mechanics to optical system. Some of the modern devices, like lasers, have principles of operation which depend on quantum mechanics. Now, quantum optics is obviously out of the scope of our syllabus, as we are not ready for it yet. Even doing exact electromagnetic theory is out of the scope of the course too. But even after that, we'll try to have a brief look into them in order to have a bigger picture of light, if time permits.